Good morning, good afternoon, good evening, depending on where you are. My name is Gerald Verbeek. I'm a member of the DFI Testing and Evaluation Committee, and I want to welcome you to this edition of the It's Money webinar. It's Money stands for Increased Testing Saves Money. And what we have been trying to do and continue to do in this webinar series is highlight case studies where it became obvious that by doing more testing, the project actually saved money, whether it's directly on the bottom line or as a result of a shorter schedule or by reducing risk. But every other month, we will highlight 3 case studies that illustrate just this concept of it's money. Before we get started, a few housekeeping notes. During the webinar, all attendees are muted. We will also record this webinar. And then after the presentations, there will be a few moments of Q&A, but the main part of Q&A will be after the last presentation, where we'll have half an hour of Q&A with the 3 presenters. And if you have a question, please use the chat box that you have in the Zoom control panel to convey those questions. And I will, as the moderator, hope to be able to ask those questions to the panelists so that we can answer all your questions. We have 3 speakers today: John Bryant, Bernie Hertlein, and Frank Jalinoos. The first speaker will be John Bryant with CDM Smith. John, the floor is yours.
Thank you, Gerald. And if I could get the control, thank you. Well, thank you everybody for attending. My name is John Bryant, and I'm going to be presenting pile load testing for pier pile reuse in Boston. I'd like to thank the co-authors of my original paper on this project, Douglas Agajan and Mike Schultz. So initially, I'm going to be getting into the project background and subsurface conditions. So the project, as you can see here in the project site, as you can see here in the lower right corner, is located in East Boston, Massachusetts, with the pier situated in Boston Harbor, directly across from downtown Boston. The pier is the site of a former 1-story naval warehouse and distribution facility that included 3 railroad spurs, 1 that ran along the center of the pier, and then 2 that you can no longer see on each side of the pier. At the locations of the railroad spurs, you see a much tighter spacing along those alignments due to the heavier loads than the main warehouse facility itself. As you can see in the photo highlighted down here, this is part of an overall development by the developer that we work with on this project to develop 7 total properties, 4 of which were going to go on the pier itself, and 3 of which went on the backlands. Previously, we had completed 3 of the buildings prior to starting on the Pier 1 foundation program. And so for those 3 buildings, they were built between 2006 and 2018 with a break for the financial crisis. The foundations for the buildings were 14-inch driven square concrete piles, and they were driven down into the glacial till and weathered bedrock layers that were below the fill and Boston blue clay. At this site, as I'll discuss a little bit later, these piles were driven a little bit deeper than what will happen for the pier, as the thickness of that Boston blue clay layer is much greater than in the actual harbor itself. So getting into a little bit of a history of the pier itself, the picture here on the right shows the pre-existing conditions from the early 2000s after the warehouse facility had been demolished, as well as some existing structures on the waterfront. This area was ripe for redevelopment, and so not only did the single developer for this property, but other developers have begun building luxury apartments right on the water due to the amazing waterfront views of downtown Boston. The pier itself was founded on driven 14-inch diameter concrete-filled steel pipe piles. However, similar to most piers of this age, it's difficult to find detailed design data about the piles themselves, as well as any pile installation criteria. And so during design, we had no actual idea of what loads were installed to. However, we do know what the building the building footprint was. And so we were able to back out an approximate pile capacity and assume that these piles were installed well over the required capacity compared to what the actual service loads for the structure were. The one item that we were able to find was an as-built pile location plan that showed the embedment depths of all piles across the entire footprint, as well as the test boring data from the original 1950s investigation that had a total of 9 test borings spread across a 3x3 grid. Additionally, during our initial design, preliminary design, we also drilled 8 borings around the exterior of the structure, including 3 on each long side and 2 on the short side, to help us confirm the previous installation data. Based upon the as-built pile location plan, we were looking at pile pier tips between about 95 and 135 feet below the pier deck. And using the previous and existing information, we overlaid the subsurface profile with the pile locations and determined that all of the piles bared in either the glacial till and or weathered rock. So looking at the subsurface conditions, you can see here on the right, we have an initial subsurface plan from our preliminary design back in 2012. For that, you see a very typical profile of what you see in Boston with fill that has been backfilled to gain additional land in the harbor, Boston blue clay, the glacial till, and the weathered bedrock. The fill itself was about 5 to 30 feet thick and consisted of soft silts. The Boston blue clay, as you can see in the figure on the right, had mostly weight of hammer material, which you would expect, and ranged from about 30 feet at the inside of the harbor to about 90 feet deep at the sheet pile wall. Then finally, you get into your bearing strata, which are typical of this region, where you see glacial till with very dense sands, gravels, and fines with mixes of cobbles and boulders in some locations. And that layer was about 70 to 120 feet below the pier deck. And then finally, your weathered bedrock that consisted of highly weathered fractured siltstone. And for this image that you can see on the right, it shows both weathered rock and bedrock. This is a preliminary figure. And once we did a detailed evaluation of the rock cores and did some unconfined compressive strength testing, we determined that this was more of a weathered rock layer that was coreable. And so we redefined that in our final report to weathered rock. And this was encountered anywhere from about 100 to 130 feet below the pier deck. So getting into the development of our load testing program, we had to look into the building code for the criteria for the reuse of the existing piles. And since this project is in Massachusetts, they have a slightly more strict building code than many other states and commonwealths, and have supplements to the actual building code itself. In general, there were 4 requirements per the building code: to not adversely affect the piles by the demolition, that the piles are structurally sound. And as you can see here in the image on the right, there was significant corrosion over the 7 decades that these piles had been installed, at least at the water line, that they have adequate structural loading capacity, and that it meets all the requirements of the building code. So teaming with our partner, McLaren Engineering, who was the structural engineer on the project, we performed a 3-phase program to determine feasibility of reuse of this pier. The first phase was a structural inspection of the existing piles above the mud line that included using dive teams to look at the piles below the water surface, as well as teams in boats and to view the piles above the water surface. Once the structural team was able to finish their inspection, they went into the development of a structural pile repair plan that I'll go into a little bit more detail on later. And then finally, we performed our load testing program, which is really the main point in this presentation. So we'll go over the structural inspection a little bit quickly. And so for the steel casing corrosion zones, the structural engineer identified 4 specific zones, 2 of which were the most severe locations. And these involved areas that you saw a lot more wet and dry cycles than the other zones. So the splash zone was the most severely corroded, where the 1/2-inch thick steel casing was corroded to as little as 1/8 of an inch in some locations, and at least 1/2 an inch across the entire splash zone. And so this was, we had seen this in the majority of the piles. And as you can see here in the upper right-hand corner, the corrosion was pretty severe and would have could potentially affect the structural capacity of the final elements. Additionally, in the mean low water zone, we saw similar severe corrosion with corrosion of typically between about 0.2 and 0.3 inches, so about 40 to 60% of the pile of the steel thickness. And then finally, we get into our tidal and mudline zones that had less corrosion since there were less wet and dry cycles of these, but we did see marine growth due to the fact that both of these areas were below the typical water line. So for the structural pile repair plan, you can see the repair plan prepared by the structural engineer on the right here. The repair was determined to be conducted in both the splash zone and the mean low water zones, where we saw typically greater than 50% corrosion of the pile itself. For these corrosion zones, the repairs were prepared for a 75-year design life for these structures. And the repair itself consisted of demoing the existing pier deck and pile caps, removal of the loose corrosion and growth in these tidal zones, which consisted of air blasting above the water level and water and sand blasting below the water level. Upon completion of the cleanup of the pile itself and removal of that loose corrosion, we installed 18-inch diameter, half-inch thick steel pipes and sleeves over the existing piles. And then the annulus between that was grouted with concrete and with grout and packers in order to have a quality seal between those piles, and was tested by the structural engineer. And ultimately, the structural pile repair for these repairs was 300 kip capacity. So now I'll get into the geotechnical considerations. So the first consideration we had was what type of load testing we wanted to conduct that was economical for the project, since this was more of a feasibility study prior to a final design to determine if the entire pier was capable of being reused. And so for the static pile load test, we looked and saw that our typical factors of safety were 2.0 per your usual IBC. But one of the main factors that led us to not use the static pile load testing was that we would have to either include 4 reaction piles, which would consist of demoing out the deck at 4 additional locations for each test pile, or use a large dead weight across the entire structure. And so due to both cost concerns with having to remove additional sections of pier deck and time constraints potentially with that as well, we determined that static pile load testing was not proper for this project. Next, we went into the dynamic pile load test, which is obviously typical of most of our projects that use driven pile foundations. For this, because we're in the state of Massachusetts, or the Commonwealth of Massachusetts, and the building code requires a factor of safety of 2.5 due to the dynamic load test is not considered a direct measure of pile load, very similar to the AASHTO codes. And so for this reason, and due to the concern that we may have some issues with some of the piles themselves due to their age, we determined that we wanted to use both dynamic pile load testing in combination with rapid load testing in order to reuse the piles without significant issues should loads be close to what we're looking for the design loads. And therefore, we ended up deciding that we would use rapid load testing. And for the rapid load test, you can see here we have these reaction masses here that totaled about 33 kips for this project. We ended up using these reaction masses in the rapid load testing test frame in order to conduct our dynamic load tests. Additionally, for the rapid load tests themselves, we were able to use a building code factor of safety of 2, since this was a direct measure of the force imparted upon the pile, and that it's a very compact load test setup and mobile test frame. And so for schedule concerns, we were actually able to conduct one series of dynamic and rapid load tests per pile per day. And so we were able to do the actual load testing within 3 weeks. So for the pile top preparation, we saw cut a 6x6 foot opening in the deck and then cut off the pile below the concrete deck about 1 foot. Divers then completed their repairs of the actual pile itself and then installed a 2-inch thick steel plate that you can see here in the blue that was welded to the top of the pile that was able to impart the force over a uniform area so that we didn't have any issues during the pile load testing. And then the pile Then the installation equipment itself was brought up with your typical pile extender, cushion, and follower. So getting into the actual pile load testing program, we had a two-phase program since we did not know if this was going to be an economically feasible project. And so the first phase was just to determine whether or not these piles could potentially be reused. And because both the owner, who is Massport for this project, and the developer, Roseland, did not want to pour a significant amount of money into a load testing program, should the piles be beyond repair, it was determined that we do an initial program with 2 test piles that would consist of loads of 200 kips, which was the minimum financial feasibility for the project, and 240 kips that allowed us to gain some efficiencies and reduce the cost for both the owner and the developer. And with this, we determined that we would use rapid and dynamic pile load testing at each individual pile location. And the purpose for this was that should we end up needing to use the dynamic load testing, that we could correlate the test results between the rapid and the dynamic load test to hopefully get a factor of safety of 2 should we need that additional capacity out of the ultimate loads. Once this was complete, obviously, since we're presenting on this topic, we ended up having a successful phase 1. We went into the detailed evaluation. And the purpose of the detailed evaluation was to do more of a parametric study across the entire pier footprint instead of 2 individual locations, to make sure that the pile capacities were acceptable, not only in the areas where we had the deepest embedment into the glacial till and weathered bedrock layers, but also shorter embedments in those layers, shorter piles versus longer piles, and things of that nature. And so for this particular portion of this, we ended up doing 3 loading intervals: 200, which was the base load that we had discussed before, the 240, which resulted in some cost efficiencies, and then ultimately the 300 kips, which was the maximum load that the structural engineer permitted per their design. And so for this program, to save some money, instead of doing the rapid load testing at all 10 pile locations, we determined that we would do it at the first 2 pile locations and then do dynamic testing only at the 8 remaining locations in order to save money from the setup of that rapid load test itself. So getting into the results of the program, for the phase 1 load test data, we used sonic echo method testing initially just to determine if there were any significant defects in the pile. And should there be a significant defect in an individual pile location, we had alternate locations to go to that we would address at that time, but we did not need that for the phase 1 program. One item of particular note for the phase 1 program was that we ended up getting a pile tip reflection from the sonic echo method testing for test pile 2 that corresponded to the approximate as-built pile tip elevation within plus or minus 2 to 3 feet. We did not see that at test pile 1. However, it did not note any significant defects, so we moved forward with that test. So in particular, the results showed that the dynamic load test ended up getting about 350 to 400 kips allowable for the 2 piles. And that is obviously well in excess of the 300 kips we were looking for. And part of the reason for this is because we were using the dead reaction masses as our driving force. We ended up using 6, 12, 18, and 24-inch height intervals for the drop weight. And so the 18-inch increments were slightly below the required load of the 300 kips. And so we ended up increasing it to 24, which significantly increased the load imparted on the pile. And we backed that off in the phase 2 investigation. Additionally, for the rapid load test, we hit our 240 kips in the second test pile, and we're just slightly under, less than 1% in the first test pile. So these results gave us confidence that we could move forward into phase 2. The pile sets, when we look at those, were less than 0.1 inches, which would indicate that the piles were driven into the soil and weathered rock, and probably did not have their full resistance mobilized, since we did not see significant movement. So some of the overall conclusions from the phase 1 were that with the dynamic pile load testing, we're actually able to exceed the full structural design loads by up to 33%. For the relatively low pile deflections and sets, it was determined that we can likely get additional geotechnical capacity out of this location, or out of these piles themselves. and that the piles reuse was feasible and we could move on to the phase 2 pile load testing program. So for the phase 2 pile load testing, similar to phase 1, we performed the sonic echo method testing across all of the piles. One good thing to note was that we actually were able to see that 9 out of the 10 test piles that we had toe reflections within plus or minus 2 to 3 feet of that as-built pile tip location plan. So it shows you that the records from this previous location or from the previous data were actually fairly accurate. In addition, we did not see any significant pile defects that were associated with these piles. So getting into the load test results themselves, for the piles with the dynamic load testing, we saw between about 270 and 375 kips of allowable load based upon the factor of safety of 2.5. And I'll get into on the next slide a little bit of why we didn't get the 300 kips in every pile. And then for the rapid load test, we were able to get 360 kips and almost 400 kips of load, which proved again that we had significantly little defects in these, or that we had significant capacity out of these piles. For the pile set itself, test pile 4 was the one anomaly where we got up to about 0.3 inches of movement, which is still well within the limits for this structure. And for that, you should note that we tested that pile in the rapid load test here to about 400 kips. So that's about 30% higher than the design load, which obviously makes sense that we're getting some additional movement. And then the remainder of the pile, similar to phase 1, ended up seeing sets of less than 0.15 inches, indicating that they could achieve additional capacity. So diving into the dynamic load test a little bit, 4 out of the 10 piles achieved their design load of 300 kips. However, 6 out of 10 did not. For 3 of the test piles, we were within 5% of the ultimate load and within 10 kips of that required load. And so as you can see there, we can definitely understand that these piles would well exceed the capacity required. For the remaining 3 test piles, 4, 5, and 7, we were a little bit lower, about 10 to 11% lower than the ultimate load. And the main reason for this was because we had such high loads in phase 1 with the 24-inch drop height that we did not want to overstress these piles and lose any monetary contribution to the final structure that the owner would realize. So for the pile sets in general, these were less than the 0.3 inches as discussed. And so in our final report, we determined that these were lower bound estimates of total capacity and that we could get significantly higher loads. So getting into the final conclusions, the soil and weathered rock resistance were not fully mobilized, as we can see through the PDA data. When we looked at the PDA data, as you would assume with the Boston blue clay, it did not have a significant contribution to the actual pile capacity, and that the glacial and these piles were likely driven both into the glacial till and through into the weathered bedrock due to their low pile sets. One other main component here would be that if we did end up testing these piles to a higher load cycle for the rapid load test or a higher stroke height for the dynamic load test, that we would see significantly higher loads. But for a project like this, you may be, and other projects, you may end up seeing capacities that are limited by your structural design and not your geotechnical capacity. The one other item that I would like to note before I get to the acknowledgements is just the overall cost for this program. So the total cost for the pile installation itself, or the pile load testing itself, was approximately $1 million. And for the phase 1 program, since we had the initial mobilization and setup costs, it was about 1/3 of that total. And for the phase 2 program, it was about 2/3 of that total. And just gives you an idea of the order of magnitude for this testing program. So just wanted to get into some final acknowledgements and show an image of what one of the final renderings may be. So the owner of this project was Massachusetts Port Authority. The developer was Rosen Residential Trust. And then we worked hand in hand with the structural engineer, McLaren Engineering Group, on this. And then finally, the dynamic and load testing firm was Geosciences Testing and Research of North Chelmsford, Massachusetts. And the SEM and rapid pile load testing were AFT out of Florida. And I would like to note that for a project like this, we ended up working fairly closely with the 2 testing companies in order to get approval from Massport for our modified testing program. And so for projects like this, it is definitely good to have an overall design team that works well together and not just stay in your silos. So appreciate being able to present this to everybody, and feel free to open it up to questions. Thank you.
Thanks, John, for a very interesting presentation. We will come to some of the questions either in a minute or at the end of the third presentation. But I would like to go one step back to what you just said before you went to acknowledgements. You mentioned that they spent about $1 million worth in testing over phase 1 and phase 2. Obviously, this testing allowed the reuse of the foundations, and that's obviously saved a lot of money if you had to install new foundations. Do you have any idea or order of magnitude of what it would have been to install new foundations for this job, so that we can see whether this $1 million was money worthwhile spent on this testing?
So in terms of the foundations themselves, we will require some drilled shaft foundations to help with some of the lateral loading from seismic and wind conditions due to the height of these structures. But I believe from talking with the owner that it saved them approximately 50% off of the foundation costs that they would ultimately have. Given that this is through a developer, we were not privy to all the detailed information, but it did provide significant savings on the foundations. Okay.
I appreciate it. You cannot always disclose the information, but I think it's important for the people attending this that obviously the owner was satisfied. It was money worth well spent. So we can assume that the investment made perfect sense. I have one question that came up, and we have time to do that already now. In your signal matching on the dynamic load testing that was done, did you detect any defects along the tested piles?
So from the PDA testing, the signal matching was very well. We did not see any significant defects. You did note some in the areas where the two pile repairs were conducted, a slight mismatch in the signals, but that was obviously due to the repair itself. And so below the mud line, we did not see any deleterious effects from the time that those piles have been installed over the last 70 years.
Okay. And then a final question before we go to the next presentation. What criteria of the design and failure sets, respectively? You indicated the pile test sets less than 0.3 of an inch, but some cannot meet the design load. Please clarify.
So in terms of the pile sets and the design loads, the ultimate design load that we were looking for the highest level of cost savings for this project was the 300 kip axial load from the structural engineer. For the dynamic tests themselves, we ended up seeing 6 test piles where we were slightly below, 3 of which were less than 5% below the actual required loads for that ultimate design, and then 3 of which were up to 10% below. But because we saw those low pile sets, we were able to determine that with additional loading that we would see higher capacities in these piles. And so when you ended up looking at the average across the entire pile group, we were looking at about 325 kips for your average pile loads across the entire set. And of particular note, the one pile that did set the 0.3 inches, the dynamic test showed about 10% under the 300 kip load, but the rapid load test that we performed ended up going up to 400 kips. And so it shows that it really depended on that stroke height. And then if we had increased it to the 24 inches from the 18, we would have likely had well in excess of that ultimate design load that we were looking for.
Okay, thank you very much. And once again, thank you for this very interesting presentation. And we'll hear more about it at the end of the 2 other presentations. But now it's time to move from Boston to Chicago. and Bernie Hertlein will start talking about some of his experience with the reuse of foundations in an urban redevelopment. Bernie, the floor is yours.
Thank you, Gerald. The sustainable movement, for want of a better word, is taking a firm hold of the deep foundations discipline. And for urban redevelopment, there is a lot of questions raised about whether whether deep foundations from existing structures should be replaced or reused. One of the reasons for this, why we're even thinking about this kind of challenge and the risks, is simply the density of modern cities. This is Chicago. You can see there's not much that hasn't already been built on. It's very rare that you find a piece of land that hasn't already got something buried underneath it. And the challenge is it safe to reuse it? Obviously, there's a lot of people that are very concerned about the risks of reusing an unknown piece of structure to support something like the buildings you see in this photograph. Existing foundations vary. As I said, most urban redevelopment projects encounter them, and they usually conflict with the proposed new foundation design, particularly like in the Chicago area, where bell shafts are fairly common. You can't just drill a hole beside an existing foundation to put in a new one, because the chances are you're going to bump into the bell. So these things have to be identified and planned for. Removal and disposal costs are often prohibitive. You're talking about trucking material out of a city like Chicago. It's not a cheap prospect. And reuse, where practical, obviously offers financial and environmental benefits. And the environmental benefits are something that I want to focus on a little bit here, because they don't often get considered or mentioned, but they are very real. The reasons for examining foundations the way we do is because the designer needs to know about the durability and the capacity. Can he use it? What sort of loads can he put on it? And how reliable is it? To estimate some of these things, a lot of other information, corollary information, is needed. First of all, what type of foundation is it? In Chicago, we've got all sorts, from the old timber foundations through sheet piles, steel tube foundations, steel pipe, concrete filled steel pipe, precast driven piles, drilled shafts of all shapes and sizes. We need to know what depth. As I'll show you later, Chicago's got a pretty complex soil system, and the depth is a critical piece of the clue, one of the critical clues when it comes to estimating the capacity of a foundation. The condition of the foundation needs to be known. If it's steel, is it corroded, as John showed earlier with the files in Boston? Is it concrete? Has it been suffered from any kind of degradation? If it's timber, has it rotted? All these things, in many cases, dependent on the soil conditions, so we need to know those too. So an integrated approach is what's needed. There are a number of invasive methods we can use, like the crudest one is simply pull the foundation out and take a look at it. Not always practical, especially with the larger foundation. Digging test pits. This can tell you something about the soils and the foundation, but only near the surface. It's difficult in most areas to dig deep test pits without significant shoring, water control, etc., etc. So test pits are very limited in what they can tell you. Soil borings are helpful, but how many can you afford to do over a large site where you know the soils are likely to be complex? That's where CPT soundings come in. CPT soundings correlated with soil borings can greatly extend your knowledge of the soils and give you a much higher confidence level of what you're standing on. And the pressure meter. This is something that's, I don't want to call it new, but it's not very well known to many engineers. But it does give you another critical piece of information about the soils at depth. Again, I will show later. Non-invasive methods for assessing foundations. There are some non-destructive testing methods out there. but the proper use of those requires knowledge of how they function. We'll come to that shortly. Proof loading. In many cases, as in the case of the Boston foundations, you can test them, load test them, and satisfy yourself as to what it can take. In some cases, the demolished building, if you know enough about it, can be considered a proof load. You know how the foundation behaved with that much load on it. So can you use that in your future design calculations? Now, the non-destructive testing is one of the less understood things here that I'm going to spend a little time on, because it's essential to understand the principles in order to have realistic expectations of what the test is going to tell you. There is no silver bullet. The simplest methods are the impulse methods, where basically you instrument the top of the shaft and tap on it with a hammer. The simplest of these is the sonic echo. Somewhat more complex is the sonic mobility, which does a frequency analysis rather than a time-based analysis. And then there are the acoustic methods. Parallel seismic relies on the propagation of a sound wave down through the foundation. Cross-hole sonic logging generates a sound wave through the foundation horizontally. And the electromagnetic methods come into it. We have the magnetometry, which is just what it sounds like. It's a magnetic detector that can be lowered, scanned over the surface or lowered down a borehole, or in some cases, ground penetrating radar. It has its uses, but it's very limited in this particular application. And we'll take a look at the physical properties of these methods, physical principles, to get a better understanding of what may help you and what won't. The impulse echo, nice simple method, originally developed for precast driven piles in uniform soils, in which situation it functions very well. It does need access to the top of the shaft. You have to be able to tap on the top and instrument the top with a receiver to be able to perform the test. So if you're under a grade beam or large cap, you would have to remove that to be able to get out the shaft. It's very fast and economical to perform, but the only information you get out of it is actually the length of time it takes for the echo or for the stress wave generated by the hammer blow to travel down through the foundation and get reflected back to the receiver. If you make an estimate as to the velocity of that wave in the material that the foundation is constructed of, you can estimate the depth. So you're only getting that one piece of information out of this. Because of that, it's not good in complex soil strata or where the shaft cross-section varies, because each of these generates a reflection too, which can complicate the result and make it difficult to identify the true response from the base of the foundation that you're looking for. It also has a limited penetration depth. This is a very small amount of energy, and it gets dissipated as it travels down the shaft, thanks to Poisson's ratio. The side friction on the shaft dissipates this energy. And typically in a soil like Boston or Chicago, medium to stiff clay, penetration depth of about 30 diameters is realistic. Anything more than that becomes very difficult. Principle is simple enough. The tap on the top of the shaft, as I said, there's the impact from the hammer. The wave travels down through the shaft and gets reflected back to the surface where it's detected by the receiver. So you measure that time. If you know the velocity of the wave, you can estimate the depth. Beyond about 30 diameters, you get nothing. The signal is completely damped out. There are some techniques that apply an amplification to the wave in this area, exponential amplification, to try and bring out the toe response. But the soil is a very noisy environment, particularly in a big city. So you're also amplifying all that noise, which again can make it very difficult to pick anything useful out of the signal. The impulse response method was developed to try and address some of the shortcomings of the echo test. In this method, the hammer is instrumented with a force transducer. So we now know the amount of force that's being put into the foundation, and the velocity, the geophone is giving us the measurement of the velocity that we get back. So from that, we can do a network analysis and calculate things like the dynamic stiffness of the foundation and soil complex, and it gives us some clues as to the concrete quality. It's very sensitive to the shaft head condition because of the force transducer. If the head crumbles as we hit it, if the concrete's cracked or broken or contaminated, it'll distort the force measurement, and so it will skew the response when we try to calculate stiffness. It's still sensitive to surrounding soils in the same way that the impulse echo test is, and it's still not very good with multiple reflectors. Same limited penetration depth, but we get extra data because of the force measurement that enables us to do a frequency analysis where we get several pieces of information out of the curve instead of just the time. The slope at the beginning of the curve helps us calculate the dynamic stiffness of the pile soil complex. Resonant peaks are generated by the reflection from the base. So the spacing between those enables us to calculate the depth of that the reflections come from. The P to Q values here, the peak and trough values, are a function of the side friction on the shaft, of the damping of the shaft. And the location of the first peak relative to the origin, the phase of the signal, helps us to determine approximately how much of the bearing capacity is generated in end bearing and how much is in side friction. The mean height of the curve is a function of the cross-section area and the concrete density. The upper and lower bounds are marked here for typical upper and lower range of concrete quality. If the concrete is less dense than expected, this curve will rise. If it's more dense, the curve will be lower. Likewise, cross-section. If the cross-section is oversized, the mean amplitude will be low. If it's undersized, it will be high. So all that information can come out of a good test result. Even in complex irregular soils, we still get more information than we would expect to get from an echo test. The parallel seismic method. This was developed to work in situations where we can't get at the top of the shaft under an existing building or structure, for example. Historic structures, commonly in Chicago, they try to save a historic facade. So we need to know what's underneath it, but we don't want to damage the facade. So in cases like that, a borehole is sunk down beside the foundation, lined with a PVC tube that's filled with water, and then an acoustic receiver, a hydrophone, is lowered into the borehole. And we strike on the top of the foundation with a hammer to generate a sound wave that travels down through the foundation and radiates out to where it's detected by the receiver. It only estimates the foundation length. It's not an integrity test, but it's there to help us estimate the length of the foundation. Because we're measuring the time taken for that wave to travel down, and we know the distance from the amount of cable we've got in the hole, we can calculate the velocity, which helps us identify the foundation material. Timber, concrete, and steel all have very distinct velocity ranges. As I say, it was developed specifically to use on existing structures. Its cost is somewhat higher than the other tests because it needs the access tube drilled in beside the foundation. Because of that, it's also slower than the impulse echo or impulse response because the transducer is lowered in uniform increments down the shaft as we generate a hammer blow at each increment. So it takes quite a bit longer to perform. The kicker here is that it's a test that may be inconclusive in granular soils or fill materials because we're relying on the propagation of the sound wave from the foundation to the access tube. The granular materials do not conduct sound as well as a cohesive material, so the test may be inconclusive in those conditions. The data is stacked for each hammer blow. We stack the data in this form. So there's the point of transmission, the impact, there's the point of reception. So again, we're measuring the time. As each blow is stacked, that time increases as we travel down the foundation in a uniform manner until we get past the bottom of the foundation where the signal is now traveling through more soil. And so the time increases. And it's this inflection point that tells us roughly where the base of the foundation is. The resolution of the test depends on the spacing of your test increments. It's usual to perform an initial test at, say, 2 foot spacings, and then go back in and repeat it in this zone at 1 foot or 6 inch spacings to try and zero in a little bit on where the base of the foundation may be. And a cross-hole sonic log method, it's usually in tubes that are pre-placed or precast in the concrete, but it can be used in core holes in an existing structure. It's been used to evaluate dams, mass concrete foundations, and large diameter drilled shafts in this form. A transmitter and a receiver are lowered down adjacent boreholes, and the transmitter emits an ultrasonic pulse that travels through the concrete to the receiver. The test is repeated at discrete intervals as the transducers are raised up the shaft, so we can build up a vertical profile of the time, the transmission time through the concrete, which is a direct function of the concrete quality. Measuring the ultrasonic pulse velocity of the concrete, which is a function of the modulus and density of the material. The depth is limited only by the cables that you can lower down the hole. It has a good horizontal range, more than 10 feet for most modern equipment, so it can be used to assess things like slurry walls and secant wall, secant wall structures. It is, however, sensitive to the tube coupling to the surrounding concrete, which in the case of existing foundations isn't a problem because you're probably going to be working in core holes. But the test is performed in this manner, the point of transmission, the point of reception. So again, the time is what we're concerned about mostly. We get this waveform where the wave is received like a chirp. But if you're on a deep foundation and you're testing every 2 inches, you're going to get 500 or 600 of these chirps. So you want a way to present them where you can, graphically put them on a sheet of paper and understand them. The easiest way to do it, or my preferred way anyway, is to do a rectification on the signal where each positive peak is printed as a dash, each negative peak is a gap. So this dot dash line gives us all of the timing information and some of the amplitude information out of the raw curve. The lines of data are stacked consecutively as we come up the shaft. And so we build up this vertical profile of the time, transmission time through the concrete. Excuse my throat, sorry. So this helps us understand the concrete quality. Any significant reduction in concrete quality will result in the curve, these lines curving away to the right. And it's quite a graphic representation because we've measured, again, we know the depth of the probes in the tubes, so the depth measurement is quite accurate. Borehole gradiometer. This is, like I say, a magnetic detection device that has its uses where there's steel involved, steel sheet piles, heavily reinforced drill shafts, etc. Gradiometer can be used to try and detect the bottom of the foundation. I say try because there are other magnetic anomalies in soil, particularly where there's fill involved. So interpretation of the Schonstedt is not a simple matter. Because of that, some people have tried to use radar in boreholes and on the surface. Problem with radar is that it's measuring the dielectric constant of the material, and any significant change in that dielectric constant generates a reflection. Steel embedded in concrete provides a very strong reflection, which, if you have grade beams or caps in place, it can help you identify where a foundation is, but you won't get through, you won't get much information through the foundation because you're going to get reflections back from the steel. The antenna transmits a microwave impulse basically down through the concrete. It gets reflected back from changes in the dielectric constant, in this case the reinforcing steel. Oops, we jump. And you can see here a very strong reflection from reinforcing steel, which creates a series of echoes and basically masks anything underneath. So you won't get any information about the underlying material in a heavily reinforced slab, grade beam or cap. Assessment of sheet piles. This has been used successfully in a number of cases. In Chicago, for example, a redevelopment site included a sheet pile wall from the original earth retention works that the contractor wanted to reuse in his new excavations. But obviously he needed to know something about the depth and condition. We tried impulse and parallel seismic test results. Both were inconclusive. Impulse response because the signal basically just got dissipated by the sheeting. The surface area relative to the cross-section area is so great that all the energy gets lost within a few feet. The parallel seismic tests showed a number of variations because there was fill material involved. We thought we saw a response from the base of the sheet, but we couldn't detect it reliably enough to be positive. So a borehole gradiometer was used also, and that too produced a number of responses, but the strongest response did correlate with the response in the parallel seismic data. So based on that, the sheets were used. The potential savings on the project were about 100,000. There has been a number of failures using this method. A most notable one was a few years ago in the investigation of the levees in New Orleans following Hurricane Katrina. One of the levees had failed and it had a core of steel sheet piling in it that was suspect. So the Corps of Engineers and Louisiana State University both performed parallel seismic testing to assess the sheet piling and reported that the piles were about 7 feet shorter than the design called for. Now, the contractor that put them in 1990 was confident in his work, so they went back there and they pulled several of the sheets and proved that they were in fact the correct length. So there was about a 30% error in the measurements estimated using the parallel seismic method. However, review of the soils in the area shows that there are several layers of shells, quite thick layers of shells in the subsoil. And that's of course a very granular material, which would almost certainly cause a loss of the parallel seismic signal. So it's very likely that the practitioners using the parallel seismic test didn't take into account soil conditions, and as a result created an error that caused quite a lot of problems for the contractor until he went and physically pulled the piles out to prove them wrong. So all of these tests needed to be used with a good understanding of their operating principle and of the factors which are going to affect them. And not understanding those factors is going to lead to certainly inconclusive data and quite often lead you completely in the wrong direction. Case history number 2 was a baseball stadium expansion, where the baseball team had got some extra income that they wanted to use. And so they wanted to put some boxes in, increased loading above the bleachers. And they needed to know what the existing foundations were, what load they could take, and would they be able to support the weight of the skyboxes, or would they have to put in new foundations? A couple of test pits were dug to check on the foundations, which were found to be concrete-filled steel pipe and believed to be step taper piles. Concrete samples were taken. Laboratory tests established the concrete strength to be within the normal range. And so the team decided to do some load tests using the structure itself for reaction mass to estimate the capacity. Testing cost was about $15,000 compared with a design proposal of 60 additional shafts at about $2,000 each, plus the cost of new pile caps and of course repairing the playing surface and all the other damage that would have occurred through such a major construction project. So total savings were estimated at $230,000. And of course, environmental savings would be not having to truck in equipment, materials, and burn all that diesel to drill the holes for 60 shafts. So it's difficult to put an actual number on it, but it certainly would have been a significant local effect. The test itself was fairly straightforward and gave us another opportunity to sample and do impulse testing on the shaft, because in the test pit, we sliced the lump out of it, put in the load test rig, and as I say, jacked it up using the existing structure as a reaction mass. Chicago is a lot like Boston in some ways, the soil particularly. As I said before, it's a complex soil structure because there's 5 distinct glacial deposits through various ice ages that affected the area, overlying the dolomite bedrock. So a number of different foundation types evolved over the years, depending on the depth, the load required and the depth they had to go to achieve the capacity they needed. The earlier concrete shafts achieved extra capacity by designing a bell, bearing on the various layers of the hard clays. There's stiff to hard clay, there's layers of dense sands and silts, and the Chicago hard pan, which is glacial till, over a rock, which again has got a layer of weathered rock over the top of the sound rock. So depending on the capacity wanted, the bells would go to various depths. The shaft could go to sit on rock, a shallow socket in the fractured rock, or a deep socket into the sound rock. Knowing which type was used is of course critical when trying to reuse the foundations. One of the earlier cases that I was able to find was by my employer, SDS Consultants at that time, which was 111 South Wacker Drive in Chicago. The original building was built in 1962 for US Gypsum, and it was shuttered in the 1990s. The basement section was turned into a 3-story parking lot, and it sat there for a couple of years until 2001. Redevelopment plans were made for the site to put in a 51-story high-rise. And the question of using existing shafts came up because it was known that the bell shafts, the shafts on this site were belled on hardpan, and they filled up most of the site. So there was very little room to put in new foundations. And so we needed to know, could we reuse the existing ones? The nice thing on this particular project was that the foundations were very well known. The design engineer at that time, the geotechnical engineer, was Clyde Baker. So he supervised the construction of the foundations for the gypsum building, and therefore had a great deal of confidence when he was asked to come up with foundations for the new 2001 51-story high-rise. One of the first things that were done was pressure meter tests to take a look at the capacity of the existing foundations. And Chicago codes have increased in allowable capacity over the years due to the amount of testing and construction verification that's been done over the last 40 to 50 years. So the pressure meter tests show that we could increase the capacity of the existing foundation from 16 KSF to 24 KSF, which was quite significant. Core samples were taken from several of the existing shafts to confirm concrete quality and uniformity. And in total, 25 shafts were reused in the main structure. So approximately, the shafts were various sizes. The existing ones ranged from 2.5 feet to 5 feet in diameter, and depths were around 40 to 50 feet. So approximately 500 cubic yards of spoil didn't have to be removed and 500 yards of concrete didn't have to be trucked in. So there again is a huge environmental saving in a city with traffic as dense as Chicago's. Not having to use all those truckloads of material was significant. The final structure also reused the perimeter wall and caissons from the parking structure, and the total savings for the project was about $1 million, which apparently in the design phase turned out to be the critical factor as to whether the thing would be built or not. Another more recent example was Block 37 in Chicago, where a previous building of where the foundations were completely unknown, and a high-rise multi-use high-rise was going to be built. So again, the foundations need to be investigated. A combination of impulse response testing and core sampling confirmed that the shafts in fact extended to bedrock, and the concrete quality was good. A combination of ultrasonic pulse velocity testing horizontally through the top of the shaft and the impulse response data, the estimated depths the UPV data enabled us to come up with a velocity for the impulse response data, and so refine our estimate of shaft depth, which correlated with the core samples and the bedrock depth. So again, a high degree of confidence the shafts were rock, on top of rock. In total, 26 shafts were used in the new structure there, with a financial saving of more than $500,000. But the real kicker was the environmental saving. Reusing the 26 shafts, the contractor's estimate saved about 2,000 gallons of diesel fuel. The shafts were 5.5 feet down and 90 feet deep, so almost 80 yards per shaft. So over 200 truckloads of spoil didn't have to be hauled out. That's assuming you're using 40-ton trucks. And 230 truckloads of ready mix didn't have to be hauled in. So again, the savings were real and the environmental benefits were significant. So in conclusion, NDT methods can be helpful in obtaining the information you need for reuse of deep foundations, but you have to understand the method and its limitations. That's critical information. Otherwise, your expectations will not be met. An integrated approach, including the geotechnical information, will be needed for accurate interpretation of the test data. And all methods have limitations. I can't stress that enough. They're wonderful tests when used in the right conditions, but using the wrong test for the circumstances will at least at the best be misleading, be inconclusive, and at worst will be downright misleading. So that's all I have. Back to you, Gerald.
Thanks, Bernie, for a very interesting presentation. And it's just kind of nice to say that the first presentation by John was more focused on load testing. You covered integrity testing, good supplement of those two presentations. And in both cases, good examples where foundations can be reused and where it made sense to reuse foundations. We'll come to the questions to your presentation at the end of the third one, because the third presentation is going to be given by Frank Jalinoos from the Federal Highway Administration. Frank, the floor is yours.
Okay, good morning, everybody. I'm Frank Jalinoos. I work for Federal Highway Administration. I'm running a lab at Turner Fairbank. It's a corrosion lab, and I previously run the NDT lab. My background is basically geophysical engineering. So let's see. It's not. No, it's not. Okay, the slides are not moving, so I don't know if I have the. Yeah, I don't. Do I have the control of the slides, Carol? Because the slides are not moving. Okay. All right. The
The slides are
Okay.
moving, Frank.
All right, so the basically outline, I'm going to talk about the whole reuse issues involved with foundation reuse, mostly in the bridge environment. I'm going to then take a look at two aspects of it. One is durability testing, which is mostly corrosion testing that is done. One is structural integrity testing with some case studies. Again, my slides are not moving. So somebody else, maybe Carol, you move the next slide.
Please click on the slide to accept control.
Okay.
Well, maybe it's better if we just if it still
Okay,
doesn't
yeah.
move. Okay,
Did
Frank.
you move? Okay. So I guess you're going to change the slides from the. Oh, okay. Now I can move. Okay, good. So foundation reuse basically involves in reusing part of or whole of the foundation as is, but often it involves evaluating the bridge for new loads. Now, on bridge environment, foundation reuse often involves the reuse of the whole substructure, the columns, because they want to keep the same span length. So that's often is the reuse of substructure involved. And in bridge environment, that's often when a replacement, a bridge replacement project or widening project or repurposing is the three main causes of this. Well, what is motivation was well mentioned in the two previous presentations. The main one is economical because they get major saving in reconstruction and demolition costs. Now, in bridge environment, you got the right-of-way issues. Whenever you have a new alignment, especially in the urban corridors, that's very costly. Utility coordination and user cost is substantial because foundation reuse is accelerated construction, so you have savings in time, and the impact on community is extensive. Bernie also talked about the environmental aspects. You don't have to go through the very extensive environmental permitting that's needed for the new foundation, the waste management, and of course, carbon emission issues that was discussed by Bernie is also implies quite a bit here in bridge environment. On the social aspects, there's a time savings. So it's a impact on mobility and traffic management, of course, work zone safety, and cultural preservation is also a big issue. So it's a big sustainability that's involved in foundation reuse. Okay, so now what are the options? I'm showing two options which does not involve reuse. This is generally what's happened in the bridge environment. Option one is you build a new alignment next to the existing one as it's done here. This is a new alignment with this steel girder bridge. So once you're done with this new alignment, you change the traffic from the old bridge to the new one, and then you start demolishing the old. Okay, so that's a kind of a parallel structure on a new alignment is option one. When you build it in place, when you demolish the old bridge, that we call option two, sometimes you keep part of an old foundation, that was the abutment here, that's used for scour, but then you build a new foundation on the back of it. So these are not reuse. This is what's done as state of practice. Now, reuse is two options. Option three is you reuse the whole foundation as is. Basically, you don't add any capacity to it. You do some repairs on it. And option four is that you enhance or strengthen the foundation. The number of options might be putting in new drill shafts or micropiles or doing ground improvement, or maybe even widening the pier cap. So these are just a composite figure showing multiple options. On as is, the example, a very prominent example is our bridges in I-95, and they were involved with 11 bridges which had to replace. So what they did is they first used they reused the foundation as is, but they did some corrosion testing and corrosion repair, which I'm going to go over it later in my presentation. And then on successive on weekends, they brought in prefabricated bridge elements, and they demolished and placed it in new section by section. Okay, so they only maybe close the traffic 3-4 hours. That's I-95, and they did it just on the weekends, and it was involved with 11 bridges. And the total saving was $60 million of reusing foundations, $60 million, quite substantive. Here, down the bottom, they enhanced the foundations by basically putting a new rebar cage. They around the existing pneumatic caisson, and they sort of widened the four piers on the river. And again here, they prefabricated the steel truss. They brought it by barges. They created these temporary piers. They put it on the piers and they slide it 50 feet into place. Okay, so they demolished the old bridge. They brought these sections of truss bridge, they put it on this temporary bridge and put it in place all in 3 days. So the impact was only 3 days replacement. We call that accelerated bridge construction using prefabricated elements. But the reuse, the net effect of reuse was $50 million in saving. So it was, again, quite substantive. But all the testing is done. It's very small incremental of the savings that is done. So these this is called slide in place type of construction. Okay, now the idea of the reuse for bridges are fairly new, but as Bernie mentioned that it's been around for buildings quite a bit, and there was a European effort called reuse of foundation for urban sites or roofless project, which culminated in this best practice guideline, which was published in 2006. It was between 2003 and 2006, basically 5 European countries. It was France, Germany, UK, Sweden, and Greece that were involved in this. And so the work is done and the best practice is published. It basically talked about reuse of small diameter piles that's done in the urban corridor, especially like in Chicago. And they even created a test site in BAM, which is in Germany, which is counterpart to Turner Fairbank. They created small diameter piles with pre-engineering defects, and they did a lot of NDTs with pulsosonic and sonic echo and parallel seismic and all that sort of stuff. So they took a look at it back in 2006. But now in 2014, on the bridge environment, we ran a workshop on foundation reuse, which created this tech brief back in 2014. 3 years later, NCHRP, National Cooperative Highway Research Program, created a synthesis of practice, what the states are doing in foundation reuse. They created this this synthesis report back in 2017. Andy Bachman wrote this, and it sort of documented what the state practice is in this area. So that's 2017. So 2014 was our workshop, and then we started a research program, which we published this report in 2018, which basically look at this whole foundation reuse in all aspects of its different chapters, starting with risk models, doing a death study, structural integrity assessment, durability and load testing, use of innovative materials, and design of new foundations for reuse. Well, today I'm just going to talk about the integrity and durability aspects of this. If you want to take a look at this document, you just do a web search, a Google search, just say FHWA Foundation Reuses, and it should be the first or second entry. You can get this report. So, okay, so what you do, the first thing you want to do in the bridge environment is do a sort of a death study. You go over all the records about the foundation and you look at the foundation performance. You look at the design, installation, soil exploration, similar to what John did in Boston. Now in the bridge environment, we also have inspection records every 2 years. Every bridge is required by us to be inspected. So those are called routine inspection, or you can have damage or special inspections if there are some special issues on the bridge, and if there are scour issues, that do underwater inspection. You want to go all the records just to see. That's the first step you want to do, including a bridge visit. Then the next thing you want to do is the corrosion study. So you start again with looking at the corrosion records on the elements that you're taking a look at. For example, you want to look at the piers as it was in I-95 projects. Then you go in the field and do some NDT inspection. That's the second step. And then the third thing you do is modeling for what is the remaining service life of the bridge membrane you're trying to reuse. So again, the process is you go out in the field, you first do a visual test, say in the column, if you have a concrete column, you look at the visual cracks or do a delamination or sounding or impact echo testing. Then you look at the corrosion or corrosivity of the element by doing half cell potential or GPR or even resistivity test. And then once you figure those areas, then you want to core into it and get the chloride profile, and then you want to do repair and get the chloride out so that it makes that component suitable for reuse. Okay, so this is the steps that taken on corrosion testing. Let's take a little bit of time. So here's a test for ground penetrating radar. You go in the column. Bernie mentioned also, so that you basically, this is a line of data. These hyperbolic events are reflections from the steel. Okay, so the tip is where the rebar is. So the time of flight it takes to go back and forth. It gives you the cover depth, which is very important because if you have areas of low cover, that's probably where the corrosion is happening. Whenever you have chlorides or moisture or corrosion products like rust into the concrete, that makes it conductive and that attenuates, damps the signal. So, and that's the area that's probably corrosion is happening. So that's shown here, or you can just simplify it and just take the amplitude of these areas and create these heat maps, and lower amplitude areas like this red areas is where the corrosion is happening. Another test that's often done is called half cell potential. I guess I have a little delay. Okay, it's coming up. The half cell potential testing. So you basically core into the concrete, into the rebar. You connected that. It's kind of like a voltmeter, and you measure the difference in potential from the surface to the rebar, and then you map it out here. So whatever you have low values, that indicates areas of high probability of corrosion. So that's a ASTM standard, very simple but effective test that's done here. So once you figure out where the corrosion areas are, you typically core and you do a chloride profile, do lab testing at this point. You take a look at where the chloride profile is, and you do other tests like petrography, you look for ASR issues and so forth. So, and then once the core result, the lab results and field results they're done, then you do modeling for the remaining service life. Then, so once you figure out what the remaining service life is, so what is the, how are we going to repair the bridge element? The most common one is cathodic protection, where you inject a direct current to the metal, to the corroded metal, which is the rebar, and essentially turning it from the anode, which is where the rust occurs, to making it a cathode. Okay, so you're sending a current. So at that point, the corrosion process really stops. And so there's two ways of doing that, but one is by impressed current, or the other one is galvanic. You put a sacrificial element on the pier itself, so that would preferentially corrode. So this is very important protection, especially in a marine environment, aggressive environments. That at this point, especially like say down there in Boston, that might be a option for doing this to stop the corrosion to occur any further. Another method is to clean the concrete from any chloride that's in there. It's called electrochemical chloride extraction, where you inject the current to the rebar, and then you're pushing the chloride out. You put a temporary anode, basically a conductive mesh, to get the chloride, which is it's going to driven back out. So reverse the process back into this conductive medium. It takes about a month or two. This is a process that was done on I-95. Of course, the traffic was not stopped, so the columns, they basically were cleared of the chloride, and they did some patching. And then once that was done, then they replaced the superstructure. So this is similar to cathodic protection, except cathodic protection, you don't have a temporary anode, you have a permanent anode, and you put less current, about 10 milliamps per square meters. This is about 1 amp per square meters. You basically keep the the steel not to corrode. That's the threshold that corrosion doesn't happen. But you have to make this as a permanent connection. You have to have rectifiers to make sure that the current is constant, because there's temperature dependency and moisture dependency. So it's an involved process, cathodic protection, but it's well worth taking a look at, especially in marine environments and splash zones and so forth. So I'm now going to shift gear and talk about structural integrity assessments, and that typically involve a lot of NDT. I already talked about GPR and impact echo and UPV, and Bernie talked about sonic echo and impulse response and parallel seismic and the use of gradiometries in boreholes. I'm going to talk about different aspects of structural integrity using geophysical logging. To do that, we're going to have a bridge that we had in as part of our central federal land. It's close to Flagstaff, Arizona, about 40 miles south of Flagstaff. It's a federal land bridge. It has very low traffic, about 2,000 cars per day. So it's a perfect site for doing a lot of testing. It's a 3-span, 2-lane bridge. It was 104 feet long, and it was 25 feet. And the central span was 50 feet, and the other span is 25 feet. It was basically built in 1934, and it was widened in 1968, and it was widened again when we were doing the testing, and there was hence that was the reason for it. So there's two aspects of the foundation. Old foundation, 1934. I'm going to show some results, and the newer foundation, which was widened, and they use a concrete pad on top of the bedrock. I'm going to show some example. So. So that was the bridge. It was a stone masonry wall bridge. Okay, so what we did, we cored from the deck all the way through the steel girders, all the way through the bedrock, through the foundations. We put a pair of cores with each of these foundation walls. Okay, and what was the coring cost? It was about $150 per linear foot. So a 50-foot coring costs us about $7,500. So a pair costs us about $15,000. So there's a way of doing that, and there's a lot of lessons learned, but they're very effective. And you get, of course, the cores coming back. So again, I'm going to use it what's known as borehole logging, or what we call core hole logging technology. I'm going to use basically optical televiewers and acoustic televiewing. I'm going to show some examples for mapping cracks from the core holes, and looking at elastic properties using sonic and density tools, which is similar in the drill shaft environment that Bernie showed with the cross-hole sonic and 4-pi density. These are other logging, which I don't have time to show examples right now, but we look at extensively this whole idea of borehole logging. So the next slide, I'm going to show, this is shown, the first one is the optical televiewer. So we have the optical camera that you're putting in down the borehole. And the tool has a 3-component magnetometer. So similar to the magnetometer that Bernie used to correct for the changes in azimuth as the tool rotates as it goes down the core hole. And it also has 3-component accelerometer to correct for inclination. So what you have is an oriented core. So you can look at it in 360 degrees, just open it up like this. So you can see the whole borehole contact information in full oriented. And then you can get the strikes and dips of any feature that you want to take a look at. So that was the concrete pad on the new foundation, and that was the bedrock, and see the contact was pretty good. Okay, you can also use a acoustic televiewer. Here you have to have the core hole filled with water and use ultrasonic waves in kind of a sonar, and then you can get reflection back from the walls, so you can look at it ultrasonically this way. Now, if you see any vogs or issues in here, you can find what the depth is, kind of like a sonar, and as is shown here. You can also use a caliper arm, that is a mechanical arm that shows what the depth of these vogs or these components are, as is shown in here. Okay, so that's acoustic televiewer, this one here, and optical televiewer. Now on the old foundation, we found these very bunch of openings here, which was unexpected, and they were subsequently grouted by our Central Federal Land Office. So you can see it, but this is optical televiewer. This is the caliper the mechanical caliper, you can see how deep they go. And of course, in the bedrock, you can look at the strikes and dips, and these are roads diagrams. So it's a very effective technology to use for foundations. It gives you a complete view of what's going on down the core hole. The second one is what we call physical properties. So it's similar to that cross-hole sonic that Pier, that Bernie talked about. Here we have a sonic tool. Basically, we have a sonic source, which is a single impulsive source, not a resonant pulse source, and number of receivers in line down the borehole. So we're looking at the time difference as the wave travels up the core holes, so to get the velocities in place. So we get a full waveform, just similar to that cross-hole sonic, but this is, it's not as a resonant signal. So we can pick the compressional wave and shear wave. So we can pick the velocities, compressional wave velocity and shear wave velocities. Also, we have a different tool we call a compensated density that it gives you a calibrated density measurements. Now, if you have velocity and density measurements, then you have all the elastic moduli information. And so doing, you can get the Poisson ratio as the black curve shown here, as well as Young's modulus, shear modulus, and bulk modulus. So you can get all the modulus information continuously every inch from the top of the core holes down to the bedrock. Here was the moduli information, the concrete pad. This is in the stone masonry. This is the bedrock. So this is a physical property measurement, quite effective. Okay. Of course, if you have a pair of core holes, you can do a cross core hole measurements. But here you need to have this, just like that cross hole sonic logging that Bernie showed. But here we're using the geophysical, because of the distance involved. We use hydrophones and seismic sources, and then you use many different angles rather than just looking straight across. We have, for every source, have many different angles, and you can do this tomographic imaging of the whole of the foundation, including the bedrock. And these were with the issues were with the those holes that subsequently our federal land office routed in. The other option is using surface geophysical methods. If you want to look at the condition of the soil and bedrock, here we ran seismic tests just parallel along those walls, those four foundation walls, this abutment, Pier 1, Pier 2, and another abutment walls, and two cross ones. So we create this fence diagram. So you can see here that the bedrock in red, and you can see there's no issues in it, and there was hardly any dip. So of course, this was a research program. So we had a lot of research money. So we want to look at the capabilities of different methods. So we threw everything at it. We run 3D resistivity, did a lot of NDT, and that's what's all in the report. And this advantage of working in a research environment, because you're basically trying to push the envelope and trying up a new methodology. You're basically looking at capability rather than a specific need. And in that case, you have to work within the budgets within the projects, so they can't do too many new ideas. There were a lot of publications in this. This was about 5 years ago that I finished this project, but now I'm looking again on the corrosion side. If you want to look at these publications, you just do a internet study of FHW FCP. FCP was the name of the project, Foundation Characterization Projects. And then you can get access to some of these reports. These are the two federal highway reports. There was a magazine article in Public Roads, which are our magazine. We put the article in Geostrata and Aspire, which is a structural article, and a number of journal articles, about 5 on all aspects, quite a bit on load rating of superstructure, substructure, combined load rating, and all that. If that fancies your interest, this is all listed in this page. You can access those. So this is our standard disclaimer. We don't take sides or promote any industry partners, and so that's all I have.
Okay, Frank, thank you very much for your presentation. And I'll ask Carol now to stop sharing the screen. And if we then can just turn on your webcams, then we can go to the Q&A part of this whole thing. For the attendees first, you may wonder why suddenly 3 presentations about reuse of foundations. The answer is very simple. There's a committee or task force within DFI. It's a task force within the joint effort of the Testing and Evaluation Committee, the Subsurface Characterization Committee, Sustainability Committee. The task force is led by Andy Buckman, and we felt that it was useful to really emphasize the potential of reuse of foundations, which is the topic of the task force. So Andy put some efforts together to get these presentations, and that's why today you got 3 presentations on the reuse of foundations, different angles when it comes to the testing methods, obviously, but then at least you know a little bit of the background. With that, before we go further into specific issues about your presentations, I would like to go around the table to get your feeling about the reuse of foundations. Obviously, you've given a presentation. Obviously, you're involved in that. Looking back, say, the last 5 years, do you see a tendency that reuse of foundations is more widely accepted and therefore cost savings can be achieved? Or is it still something that is happening only now and then? What is the situation there? Bernie, let's start with you.
I think it's a mixed bag. Depends very much on the players in the game. The commercial market is always willing to look at these options, money rules, and if there's a way of saving time or money on the project, then they'll certainly discuss it with you. A lot of the government agencies are much less interested. They're focused solely on risk. They're not particularly bothered about saving money. Their risk is the be all and end all for them. So it's 2 very different approaches to the idea. In the Chicago area in general, we are seeing a fairly regular reuse of foundations, although some of the more recent projects have been pretty straightforward in that the new building going up was actually less than the one that was demolished. So the foundations are already considered to be proof loaded and they're quite happy to go ahead and use them. Another example, for the sake of argument, is the spire that never happened in Chicago. And that was a massive structure planned and all the foundations were constructed, very deep foundations. And then the money ran out, and for I don't know how many years, I think it's probably about 10 years, 15 years, something like that. It's just been sitting there, a big hole in the ground. They are now deciding to put up a new structure, or somebody else has taken over the project and they're going to continue and use those foundations. So whether you'd call it reuse or just simply using foundations that have been in storage for 10 years, I don't know. But yeah, it's all about risk. And most agencies are very risk averse. Commercial developers are far more willing to consider the risk as long as they can balance it with expert advice, basically. So we come in, we look at everything all the information that's available and tell them what else we need to do to be comfortable in reusing those foundations. And generally they take a pretty positive approach to it.
Okay, well then the logical next person to answer this thing is Frank, being part of Federal Highway. Therefore, yeah, as Bernie said, less or more worried about the risk and less focused on saving the money. How do you see this whole thing? And do you agree with Bernie's assessment?
Well, it's a little different on the bridge environment. Of course, the states are the bridge owners, and when they look at it, and a lot of times they take the risk if it's well founded, coupled with testing. Now, as I said, most of the foundation reuse on the bridge environment happens on when they reusing the foundation as is, or the whole substructure as is. So what they do is do a lot of corrosion testing and corrosion repair. So a lot of the work is done by the corrosion engineering firms, and my understanding they're pretty busy. So there's a lot of this is going on. So once that's done, then they replace the bridge. This whole concept, I mean, there's a substantial amount of savings in the bridge environment because of the environmental and all that. You don't have to go through the geotechnical and hydraulic analysis again, and that's what's a very high savings. So that saving can go into. It also pairs well with this accelerated construction idea that I showed a couple of projects where you prefabricate bridge elements offsite, kind of like manufacturing, bring it to the site, and you basically replace a bridge or widen a bridge with minimal impact to traffic. So that works very well in interstates and urban corridors like Boston areas. There's about 11 bridges were replaced this way with reusing the foundation. So it's it's happening. A lot of it is not as much advertised. It's we have to ask the people in the corrosion area. But when it's involved in enhancing the foundation, that's where the geotechnical come in with new foundation elements and ground improvements and so forth. But this is something that works hand in hand. The structural engineer who makes a decision to reuse the foundation, always the first step is to work with the geotechnical engineer, look at the performance history of the foundation. And I didn't talk about load testing. As Bernie said, we talk about this idea of a proof load testing. So you go to the supports and you bring in the new loads and you incrementally add it up to the existing load, and just to see how much of a movement you get on the supports after you enhance it and so forth. So it's a kind of like it's a proof load testing that we can do. I mean, already the foundation is proof load tested because it's been carrying the load, but you can bring the replacement load as well. So it is going on. I don't have the exact idea. The synthesis, which was published by Andy, he sent the questionnaire to all the geotechnical. So those were reuse cases that involve a lot of geotechnical work. But there's a lot of other, probably a lot more reuses happening by, again, the corrosion engineers, which they just they do testing under the guidance of the structural engineer. So I have been out of this research for 4 years now. I'm getting back to it in the corrosion aspects of it. So I don't have quite an aspect of exactly how much going on, but whenever we had a workshop at the TRB, the Transportation Research Board, and we had like 3 different workshops, the room was filled. So I would say the interest is there.
Okay. John, what's your take on the reuse of foundations? And also, of course, in your case study, you talked about something that happened on the edge of Boston, across downtown Boston. Therefore, there was some more space. Do you see that in downtown Boston, where there's, again, space limitations, that there's a different approach to this whole thing in some of the outlying areas?
Yes, I would agree that, especially in these urban areas like Boston, Chicago, and others, we have been seeing more, especially on the development side, like Bernie said, more appetite for the developers to reuse existing foundations when there is enough existing data. I know that for our project, having the as-built for the pile location plan really did help push the developer as well as the owner to have more comfort in the fact that these foundations were installed to high quality loads. When you're looking at our project in particular, we only had a one-story warehouse, and so you would think that these foundations wouldn't be installed to these significantly high loads, but due to the design criteria back in the 50s, they may have driven significantly more piles into deeper depths than we made today for cost purposes. And so on the other side of things, I would agree that for public clients, we do a lot of work for city and county entities that have water resources, water and wastewater resources right by rivers. Those entities are a little bit less risk tolerant, and so they need a little bit more information where they would need that detailed information. in order to move forward with actually redeveloping those properties with the same foundations. And so really, I think it comes down to the risk tolerance of the developer, as well as a combination of how much existing data you can provide, especially from the geotechnical standpoint, to feel comfortable that we can reuse these foundations properly.
Okay. Before we go to some more general questions, there are two questions that have come up based on presentations. One was for you, John. Was any additional pile testing recommended as a result of the outcome of the pile testing program to be performed then during the actual project execution?
No, so for our project, the structural engineer during their preliminary design had a really good understanding of what their final foundation loads would be. And they had multiple different scenarios where we'd have either 5 or 7 story buildings where they were able to figure out what the loading conditions were. And so due to the high upfront cost of the mobilization of the equipment, where the testing platform was actually being shipped up by barge from Florida to the Boston area, having to go back and do additional testing would have been too expensive for the owner as well as the developer. And so we made sure that everything was on the upfront, that we were doing everything we needed to for final design. Additionally, we got significant more comfort from what you saw in the test results that these piles were installed to well in excess of the axial capacities that we required. And so by overlaying that data onto the load tests that we saw with the pile depths, we were able to have comfort in the fact that these piles could be reused for the entire pier deck as required.
Okay, thank you for that. I had a problem unmuting my microphone. Frank, 2 questions for you on your presentation. One is regarding the corrosion potential. The question is, even if there's still some corrosion potential, the compressive capacity or capability is still there, and the lateral demand can be reduced with a few anchors or soil nails. Is this practice in place, and then is it being used?
So I guess they're talking about the corrosion potential for a half cell potential, right? Is that?
Yes.
Okay, so that's correct. That just shows the probability of corrosion, what areas are higher and lower. So that just shows where the corrosion might be occurring. On the capacity side, that's a different issue. This is just in corrosion and section loss on the steel and where areas and the delamination. So that's what we're trying to look at for the concrete, right? So this is reinforcing concrete. Delamination basically. So now, when you talk about under, structures, buried structures, which we talked about buried metal corrosion, that's a little different mechanism of corrosion than say in reinforced concrete. So if you have like a buried steel piles or H piles, that corrosion that happens normally near the top of the soils where you have a little oxygen, a little bit different mechanism of corrosion that's happening than if you're in the above the ground corrosion, especially in reinforced. So I'm not sure if I totally answered the question or but that's the gist of it. This is just the looking at where the damage or where the chlorides are, where the damage may have occurred. That's what we're looking at, and how to prevent further corrosion by doing these cathodic protections or just cleaning the whole structure from the chloride. That's the intent of this test.
Okay, but rather than addressing the corrosion potential, you could also then do some additional things, and I think that is what the question is after, is whether you could use anchors or soil nails to at least provide additional capability.
Yes, I mean you can enhance by soil nails. Yes, exactly.
Okay.
From the but here we're just looking at where the corrosion areas are. Then you have the calculation has to be made, how much capacity is undermined, and then you have to enhance it by this by soil nails or other measures. Correct.
Okay. Well, let's go back again one step or take a step back for all 3 of you. And we talked a little bit about the reuse of foundations and then the issues that are associated with that. Since you are all involved in reuse of foundations, what is this one single thing that you would like to convey to the audience and to the foundation community at large, is why reuse of foundations really should be done? Forget about whether it's reluctance there, whether it's a question of the risk, but what is really for you personally the main thing about why reuse of foundation is really a right thing to consider and why it should be promoted? And let's start again with Bernie.
Yeah, sorry, couldn't find my unmute button. I think the sustainability issue has got to become more important over the next few years. I mean, everybody talks about it, and this is our opportunity to actually do it. It's not just reusing the foundation, it's all of the collateral activities that go along with that. Like I said, for the Chicago things, you're not trucking out huge truckloads of spoil. You're not bringing in truckloads of concrete. So the wear and tear on the roads, the diesel fumes, everything that goes with it, it's all part of the environmental sustainability question. And I think reusing the existing foundations makes sense on every level, economically, environmentally, schedule-wise. It just means essentially cheaper buildings at less contamination, if you want to put it in simple terms. Yeah.
And especially, you mentioned schedule, that's something we haven't talked about much so far. But indeed, when you look at cost savings on the bottom line, and obviously a shorter schedule has a major impact. John, what's your take on this whole thing? Why would you say to young engineers or to colleagues that, hey, start looking at reuse of foundations?
So for me, from a geotechnical standpoint, barring corrosion issues like Frank is talking about, reuse of existing foundations will cause significant savings for your clients from a foundation standpoint. They're not having to go back down and build brand new pile caps. They're not having to install infrastructure that's been sitting there maybe 30, 40, 50 years that we already know what the load capacities are. And so I think increasingly along the sustainability aspects in urban areas where you have issues like Boston, New York, Chicago, with getting adequate housing, having cheaper housing costs, you're going to be able to allow developers to develop properties for significantly less cost by reusing structures that may have had foundations installed way past what the actual capacity was required at the time. And so in the end, it'll save not only the developers and your owner money, but it also will reduce costs for others in terms of housing as well.
Okay. And Frank, what's your take on this whole thing? What would you say to your colleagues among people in DOTs and in federal highway, but especially DOTs, that, hey, start looking at reuse of foundations?
Well, in the bridge environment, the reuse is very apparent because the cost savings are substantial. But what I would tell them is not necessarily promote reuse or promote extensive testing to make informed decision whether you want to reuse or not. And a lot of cases you do not. So you start basically looking at, we do inspect bridges regularly. So you look at the inspection records, look at the performance of the bridge, and we look both superstructure and substructure. So if there's any movements on the foundations, or we have all those records, and we have the inspector's report. So you look at those first, just to see if this is suitable, and you look at the plans. If you don't have any good plans and you don't know what the depth of your foundations are, we call that an unknown foundation, and you have scour issues, those probably not a good candidate for reuse. So you start those first and in kind of a depth study. And then if you decide to do that, you look at how do you, amount of corrosion. If up north, most of the corrosion happens because of the salt that it leaks through the joints and corrodes the bearings and the top of the piers. In the south, like in Florida, it's bottom up. Most of the corrosion starts from the substructure coming up to the deck. So you look at the corroded environment, and then you want to assess what the remaining service life it is based on corrosion analysis of the substructure. And once you go through that that route, then you want to look at the capacity and do load testing and see if you have enough capacity, remaining capacity for the new loads, because sometimes you replace the bridge or widen the bridge and so forth. And you might use some innovative materials like lightweight concrete, which weighs 17% less, so say on a deck, so that you keep the loads similar to what you had before, so that so you have that factor of safety. So you want to do all of this testing. You want to do integrity testing. You want to do durability testing. You want to do load testing, and you want to do field visits, and to determine whether this is a good case for reuse. But even if it's not, and there were cases that the testing was done, the savings you get out of the reuse after you do all this testing is substantial. It's the return of the investment is way out there, at least in the bridge environment. But what I'm basically promote is to look at this testing methods and try to advance the testing methods so we get better information about the foundations and the substructures and the state they're in, so that we put them into another cycle of reuse, another 50 years, another 50 years of service, or 70 years. So basically, that's one element. The other one is on the foundation side. Most of the bridges, if you look at it, our decks last maybe 20, 40 years. The superstructures maybe 40, 50, but the foundations can last up to 100 years. So and given this facts and the new foundations, like new drill shafts, where you have the large 8-foot diameter non-redundant shafts and all that, I think the new designers should bear that in mind, that these foundations designing can go to many cycles of reuse. So if they can consider some bare instrumentation of those things, just to make sure that the capacity is there, goes a long way. This is not talking about continuous monitoring. They're just putting some instrumentation in there, like strain gauges or accelerometers or whatever, just to look at structural integrity. Once you have access to the shaft, or if you're doing cross-hole sonic logging, at least keep a couple of those tubes open. You can put epoxy, make sure the corrosion doesn't happen, so that later on, if 30 years, 40 years, if you want to reuse that foundation and we want to look at structural integrity, we can do that. So the foundations of today can probably go on many, many cycles of reuse, especially the larger foundations that the drill shafts and piles and so keep that in mind in designing a new foundation. Perhaps in some projects it makes sense to put some instrumentation for the future generation, I would say.
Right. Okay, thank you. Thank you for your presentations, and thank you for answering the questions. And I apologize for the background noise right now. Somebody is deciding to do something around their office building, apparently. Carol, if you could put the slides back on again, and then we can close this session. First of all, to all the attendees, if you're interested in the topic of reuse of foundations, please consider joining the task force that Andy Buckman has. You can contact me, or you can contact DFI or Andy, of course, directly to get in touch with them. But Carol, if you could put the slides back on again, then we can close this. I can make a few housekeeping notes. There we are. First of all, the upcoming webinars in this series will be again the first Wednesday in February and in April, February the 2nd and April the 6th. And I hope you will join there for those presentations. And then if you move to the next slide, Carol. You will get PDH certificates for this webinar, and the recording will also be posted. And if you have any questions about your PDHs, because normally they should come within about 3 weeks, although this we're still early in December, but It may, because of the holidays, be slightly delayed. But if you have any questions about it, you see there the email address of Jamie Satina, the professional development coordinator of DFI. You can always email her or you can email me. And with that, if you move to the next slide, to Jamie, I want to once again thank the presenters for today. I want to thank you as the audience, because without your presence and your interest, we cannot do that. And again, if you have a topic where you say, hey, this is a nice example where increased testing did save money, as you heard today and in the previous editions of this webinar series, let me know. We're always interested in case studies that illustrate that. And with that, thank you very much for being here. Thank you again to our panelists, and I look forward to seeing you next time. Thank you very much.
Thank you.